Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking the small signal resistance in kilo ohm offered by the N-channel MOSFET M shown in the figure below at a bias point of VB is equal to 2 voltage is device data for M, device transcond parameter Kn is equal to mu n cox W over L, that is given by 40 microampere per voltage square, and threshold voltage VTN is equal to 1 voltage, and neglect body effect and channel length modulation effects. Okay, here we have 4 options. Now let's see what we are going to get. Okay, now first of all, we know that this one is the train is connected to the gate. Here the train is connected to the gate, so this will act as a two terminal device giving us variable resistance. That's why we can calculate the resistance using this formula dVb by dId. Okay, let's write this one down right here dVb by dId. Now this is inverse of transconductance. If you remember transconductance equation, that's given by Vg divided by Id, right? But here we have dVb divided by Id, so this is reciprocal of inverse of transconductance, so this is 1 over Gm. Now we are interested in calculating this one because this is the one we are going to give us the resistance. Now first of all, we have to know which region we are having right here. Now in order to look at that one, since train is connected to, like, this VB is equal to this one gate voltage, right? So here what we are going to have, we can say VDS is equal to VB. Train voltage is VB because this is train and voltage is VB. So first let's mention that one here. VDS is equal to VB, and also VGS, gate voltage, is going to be same as train voltage minus VT, and train voltage is VB, so VB minus VT. Now here we have a condition, like we can have linear region, saturation region, and we have to look at which region we are involved in. Now if you look at this one, VDS, if VDS is greater than VGS minus VT, right? This MOSFET is in saturation. This VDS is what train voltage. Now let's look at the given information. VB is given. This is the train voltage. So 2 voltage, and gate voltage also same since it's connected. So gate voltage is same. Okay, let's avoid this one. So gate voltage is what? That's also 2, and this threshold voltage is given in the question here. Threshold voltage is 1 voltage, so 2 minus 1. Here you can see this side is bigger than this one, right? So this is in saturation, so we can say MOSFET is in saturation. MOSFET is in saturation. So if the MOSFET is in saturation, we can use this transconductance equation. So when the MOSFET is in saturation, the transconductance equation Gm, that's given by mu n cox W over L times VGS minus V threshold. Okay, and here in the question we have this value. This is Kn value, mu n cox W over L, that's given by 40 microampere per volt square. So 40 times micro is 10 to the power minus 6. So we have taken care of this whole part, mu n cox times W over L, we have taken care of that one. The whole thing is equal to 40 times 10 to the power minus 6. Now VGS minus V threshold. VGS minus V threshold is 2 minus 1, that's equal to just 1. So this is just 1, right? So finally we end up with Gm, this is transconductance, that's equal to 4 times 10 to the power of minus 5. But here we are having variable resistance, and we found out that the equation for variable resistance is dV by dId, and that is inverse of transconductance. We found out what transconductance is, so we just have to find out what is the inverse of this one. So inverse of this one is what? Let's write the equation again. dV by dId is equal to 1 over Gm, that's equivalent to 1 over Gm, we just found it out, that's 4 times 10 to the power of minus 5. So 4, instead of writing 10 to the power of minus 5 in the denominator, I can write 10 to the power of 5 in the numerator, and if you divide this one by 4, you are going to get 25 kilo ohm resistance. So this is going to be the variable resistance, and the correct option for this question is B. So this is the final answer. I hope this helps. Thanks for watching.